right, so today we have Jure Leskovec. He is a professor at Stanford in computer science. And more importantly for this episode, he is co-founder at Kumo.ai, Kumo.ai. Taglines are the first foundation model built for enterprise data, relational enterprise data. Get instantaneous predictions straight from your data warehouse. Zero shot, out of the box, fine-tuned when needed. No ML pipelines required. And with that, Jure, welcome to the podcast.
Thanks for having me.
All right, so I guess we'll start at the beginning. We'll go through the solutions, your technology in detail, but let's start at the basics. What problem is Kumo targeting?
So the problem we are targeting is AI over structured business data. So, the most valuable data every enterprise has is this ground truth of the business stored in data warehouse in this structured tabular form. This is customer records, product catalogs, transaction records, supply chain management data. All that is kind of the ground truth of the business. And we are doing AI predictions, risk scoring over this type of data.
And traditionally, I would say the traditional solutions would be either you have some sort of data science team. I guess you will have a data science team. And so the question is, will the data science team build their own ad hoc data science tools internally with a data platform team? Or they can go to one of these cloud hyperscalers like Google or Azure who have some sort of data science solution. Is that correct? Is that kind of the de facto solution is sort of like this, right?
Yeah, I would say there are kind of two potential solutions, right? One solution is that you would say we have the large language models, so why don't we just textify the tabular data, throw that into the large language model, and it's going to give me accurate predictions, accurate forecasts, accurate estimates. And it turns out that works terribly, and it's a bad idea. People have tried it, and it doesn't really work. Like, next token prediction is not the same as forecasting. So then what is the today's solution, or this status quo solution, is basically let's do machine learning, which basically means let's hire a data science team. Let's engineer a number of features. Let's create a training data set. Let's train this task-specific model. Let's put the features in production. And then, let's put the model in production. The issue with that approach is that it's super manual and super expensive. It, on average, takes about 2 full-time employees to take care of a single model. More than half of these models that are being developed in industry don't ever reach production. Developing a model for a single task is like a 6-month type effort. And just maintaining these models, the production pipelines, takes a very long time, right? It's like the cost is significant. So somehow it seems that, the AI revolution skipped structured data. If you want to do something with structured data, you basically use 30-year-old technology.
So on the data science team, a few things from several years ago, right? So one is the time series libraries and the data science solutions. They tried to do some sort of AutoML, right? So they were trying to automate, but then, as you point out, the problem there is it might work, but it depends on how important the forecast is. If the forecast is super important, you probably don't want to go with the AutoML solution.
Yeah. AutoML promised a lot, but it hasn't really delivered. And I think the reason it hasn't delivered is because it's too brute force, right? It's just for loops over hyperparameters, automated feature engineering sometimes that runs arbitrary SQL queries over databases, creating humongous joins, and then, training 17 different challenger models and hoping that one of them will work. So it's just kind of a big random search over the humongous space of possibilities.
So the other more recent development, which I have to profess I don't have a good feel for. I'm a bit skeptical. Is the so-called time series foundation models, right? So where, as you point out, so there's different kinds of them. One, as you point out, just takes kind of like, here's a text model. We'll treat temporal data as if they're text, sequential data, and then hope for the best. And then there were some other people who were trying to build time series foundation models much more from the ground up. I profess I don't know anyone who actually uses this seriously in production.
Yeah, but I think that work is I like that work, right? Because
So
what
there's
that
promise
line,
there.
yeah, there's promise. What that line of work did was basically say, let's represent a time series as a sequence of tokens, and time series is naturally a sequence of tokens. So we can kind of feed in one time series to the model, and then the model is going kind of to predict it forward. And of course, you need to change the transformer architecture, you need to change the tokenization, attention mechanism, things like that. But you can pre-train, and it works quite well, right? So I think what this showed is that it's possible to do a foundation model. I would argue that foundation model for time series is somewhat easy because time series is a sequence. We know how to attend over a sequence, right? The foundation model I'm talking about is a foundation model that can be applied to any database, any set of tables, any kind of predictive task. So, it's another 2 steps forward from let's say time series foundation models that are basically meant for time series forecasting on a single time series at a time.
So on the time series
But
foundation models, I think there's some open weights ones, there's research ones, there's ones that the cloud providers are starting to introduce. And my impression, Yuri, is that it's still at the point where it depends on how important the forecast is or the task is for you, right? So in other words, if it's super important, you probably still want a data scientist to look through the results and compare it and kind of really test it. But if you're one of these if the application is like, DevOps, where have millions of time series and, maybe, alerts, maybe as long as you don't get alert fatigue, you're okay using one of these. Am I correct?
I think I'm not sure I would entirely agree with this. I think with foundation models, you are able to make very accurate predictions as well. And of course, you can have them give you these predictions almost like in a ad hoc way with a frozen model. But of course, if you really want high performance, you can always fine tune for that specific thing. And what we see, and we can talk more about this later, you get to the superhuman performance. So you can build models, predictions that are more accurate, like 10% more accurate, 20% more accurate than any human with traditional machine learning toolbox can do.
Okay, so now let's go to this notion of relational foundation model, which you point out goes beyond time series. It's basically any sort of machine learning task that involves relational data. So relational foundation model, so the phrase foundation model is in there. So is it a true foundation model in the sense of what we think foundation models are?
Yeah, so I can explain. So the way this works is that you have a pre-trained model that is frozen, that has never seen a given database.
Never seen my company's data.
It doesn't need to see your company's data. You connect this model to your company's data, to a set of tables that are interlinked with primary foreign key relations. Maybe that's 10 tables, 20 tables, 5 tables, whatever it is, right? You say, this is my schema over which the foundation model operates. And then you have a querying mechanism, a prompting mechanism, where you prompt the model with a specific prediction task. And then the model, in a single forward pass of its architecture, is going to give you an accurate prediction. Our tests show that the accuracy of this prediction is as good as a 1 month of a PhD level data scientist building a manual model. So that's what you can do. You basically say, I want to predict a 60-day churn for this particular user, 200 milliseconds. You have the answer. That's as good as 1 month of a data scientist building a custom neural network decision tree, whatever it is, for 60-day churn prediction problem. Of course, if you don't want 60-day churn, you want a 48-day churn, you just change your prompt, you get a different thing. You don't want churn based on the number of purchases. You want to say, is this person spending less than $100 in the next 3 months? You ask this, you get an answer. So basically, you can now ask these predictive questions in a ad hoc, in a real-time way, getting back accurate answers 200 milliseconds later. Of course, now if you say, but I really care about this answer to be as accurate as possible because it's so business important, you can always fine-tune the model for that specific question, for that specific data. And then you basically now have a fine-tuned, let's say, single task model that is super accurate.
So I have several questions. So the first one is somewhat of kind of a cold start question, right? So if you look at what's happening in the text to SQL space, right? So all these people, Databricks, of which I'm an advisor, Snowflake, almost all of them have this notion of, oh yeah, so we can help you with text to SQL, but first we have to build what they call the semantic layer, which is basically metadata and all of this, right?
Yes.
So I'm assuming you need some. It's not gonna work. I mean, how out of the box is it? So does it take a while for it to learn something about my data?
There are two separate problems here. One problem is, how do you prompt the model? We have actually developed a domain-specific language that looks like SQL, but rather than starts with select, it starts with predict. And then you basically, with SQL operators, you say, what am I predicting? Am I predicting, 30-day count of purchases in the future? And then you say, who am I predicting this for? So you say, for whatever entities. Maybe you are predicting this for a user. Maybe you are predicting this for a product because you are saying, what's my product sales forecast? So you have this structured language to prompt the model with. It looks like SQL, but the fundamental difference is that SQL is about the past. SQL, you ask what happened last week. Here you are asking what happens next week or what happens next quarter. So it's like forward looking. With that, you prompt the model. Now, of course, the same way as in text to SQL, where we take text and translate it to SQL, you can take text and translate that to my predictive query language. And for that, you need the semantic model. So you don't need the semantic model to make predictions per se, the same way as you don't need semantic model to run SQL queries, but you need semantic model to go from text to the predictive specification. Because if you say, predict me 30-day churn, in some organization, this means number of purchases. In other organization, this means number of clicks on the website. In some other organizations, it may mean total estimated purchase amount less than $100 or $10 or whatever it is, right? So for that, you need some kind of semantic model.
Yeah. And also, if you go into a company, right, so they could have multiple data warehouses. And to a large extent, a lot of how these analysts and data science teams work over time is they develop institutional knowledge, right? So, oh yeah, for sales in the Southeast, we should hit this data warehouse, not this one, because the data for the Southeast is better on this data warehouse. So how do you learn all of this? How does your system learn all of the metadata and institutional knowledge, I guess?
So I would say this is part of the setup process, where either this information is entered during the setup, where let's say the data scientist or the operator of the system can select what is the data, what's the semantics, and all that. I would say that we need to codify that, and that is part of the setup process for the model. And once the model is set up, now you can ask it any predictive question over that database and the semantic model that has been set up.
What is the typical setup process, Jure, in terms of if you go to like a company, how long does it take normally?
A couple of days,
Oh,
a day.
So
Yeah.
you need access to a few key people who know a lot about the underlying data.
Exactly, right. There's no way around that. We need that mainly to go from the textual description of the task to the structured prediction of the task that then is executed by the foundation model at the bottom. And then, of course, foundation model needs access to the data. So part of the setup process is to decide what tables is the foundation model using. What are the semantic types? What are the data types? And how the primary foreign key relations work.
So in the forecasting example you gave, you said, okay, after 200 milliseconds, I get a prediction, right? So why is it so fast? Because, normally deep learning and neural nets are not as fast as traditional statistical models, right? So.
Yeah, the reason why it's fast is because there's no model training happening, right? At the query time, at the inference time, the model is frozen.
Oh, I see.
So the model is frozen. The model doesn't do any parameter updates. There's no gradient descent. The model is frozen. So the way the foundation model operates is that once you specify the predictive task, the foundation model goes into the data and generates a set of in-context examples. And then those in-context examples are then fed into the model, and in a single forward pass of the model, the prediction, the forecast, the recommendation is then made. Right, so the reason this is fast because we can generate the in-context examples based on the task specification very quickly, and then send them through this pre-trained architecture without any feature engineering, without any model training, no parameter updates, to give you an accurate prediction. That's why it's fast.
So this in-context retrieval has to in-context examples is some sort of graph retrieval process. Is that correct?
That's great, right? So you mentioned graph retrieval. So the way the underlying technology works and what the key insight is that any database, any set of tables can be represented as a graph. And then if you just think about, let's say, two tables, right? Imagine you have a user catalog and a set of user transactions. Imagine you want to predict user churn, like a classical kind of boring task, right? What today you have to do, you take the user table, the transactions table, you join the two together, and then you need to aggregate the transactions per user. So you could say count of transactions last week, sum of transaction prices over the last 3 weeks, count of transaction prices over the last 2 weeks, but between 6 and 9 a.m. in the morning. And those are your features, right? But the difference here is that we can represent these, let's say, these two tables as every user is a node, every transaction is a node. And then a user points to its own transaction or his or her own transactions. And now the attention mechanism attends over the raw transactions. And because of the attention mechanism now attends over the raw events, there's no feature engineering needed, right? So it just attends over those raw events. The attention mechanism has so much more, let's say, finesse or fidelity to extract signal from the data than manual features do. So you don't need to do any data joins, no feature engineering. So you get these predictions super fast. And because they are done actually on the raw data, the attention mechanism is able to extract more signal than manual features typically do. So these models tend to be very accurate and go to this superhuman regime of accuracy.
And to our listeners, of course, this probably is years of research in Jure's group in Stanford that makes this real. So, Jure, would you consider this an example of a graph neural network then?
This a great question. So my group pioneered graph neural networks. This is the next generation of that.
Okay.
And the beautiful thing is that it's general. It's not about graphs. It's about databases.
Right,
So
right.
everyone has a database.
Yeah. Because the
You-
problem with graph neural networks has always been no one has a graph.
Nobody has a graph. But now I'm saying any database is a graph. You can now train what we call relational graph transformers directly on the raw data. And you get all the benefits of, let's say, true deep learning, right? Think of computer vision pre-deep learning, post-deep learning. Pre-deep learning, it was about detecting edges and sift features and Gabor filters, and then training a classifier. Post-deep learning era, learn directly on the raw pixels of the image. We are doing the same thing, right? Where we say, let's learn directly on your database. How do we do that? Because a database is not an image. Database is not a sequence of text. We say you represent the database as a graph, and now your neurons can directly reason over that graph. And you get all the benefits that we have already seen in computer vision, as well as in natural language understanding with large language models, who just, again, learn over a sequence. The only difference is that image is a fixed grid of pixels, text is this linear sequence, and a database is a more complicated structure. It's a graph.
So we started this out. I kind of brought in the example of forecasting and time series, but as you point out, this technology applies to relational data in general. And so I assume that I would be able to use this to do things that I would do as a data scientist. Like someone will ask me for, I don't know, churn prediction. Score the customer database for likelihood to churn, right? So in the
Sure.
past, I would have to go into the database, start gathering the features, and then build a model. There's some feature engineering. I mean, this could take weeks, right?
Exactly. So this is the traditional approach where this takes weeks. And then, it's actually much, much harder, right? Because now after weeks of work, you just built a model. Now
Right.
putting this model in production is even harder, right? Because this means that actually, especially with these temporal type problems, right? For every new event, you have to recompute all the features, right? So keeping features up to date in a production setting is super hard. And either these features get stale because they haven't been updated up to the present time, or these features are kind of have time travel issues, information leakage issues, and your models are kind of miscalibrated and mistrained, right? So that is a huge issue. The difference here is that the data scientist just says, these are the tables I wanna build my model over, and it's a neural network who takes care of time, temporal consistency, attending over the raw data to give you that accurate prediction.
So Jure, one of the painful things about data science work, obviously, is data itself, right? The data has missing values and needs to be standardized and cleaned. And so I'm assuming that your technology requires the data to be at a certain state, that it's not going to work miraculously if the data is a mess.
Good question. I think there are two parts to it, right? One fundamental truth is like, garbage in, garbage out.
Right.
Um,
And also
and
the whole notion that data science work is 80% data cleaning, kind of. I don't know, some.
I hear that. I think the difference is the following, right? It's like, as a data scientist, you are operating truly at the modeling side of things rather than at the data cleaning side of things. You say, these are my tables, these are my raw events. Yes, it might be noisy, it might have missing labels, but because the model is learning over the graph, over the relationships, these models are actually more robust to these kind of data issues.
I see.
Because they can kind of fill in missing values. Every data point is situated in its relational context, so the model can kind of learn to borrow information from nearby data points to robustify itself.
Or sometimes you have categorical values that are a mess, right? So state of California can be CA, CAL, CALIF, Uh, what can your technology overcome kind of messy data like that?
That's a good point, right? Like the way we operate with that is that it's a collaboration between the model and the data scientist, right? We would provide tools, diagnostics, and then of course the operator decides what do they want to do with like a super messy categorical column. Do they want to model that as a categorical column? Do they want to model that maybe as text? And then all these different spellings will naturally kind of naturally be able to be considered together. That's part of the modeling process, I would say.
So another task that might fall under the purview of relational data, at least in some cases, right? So you can imagine you're an e-commerce site, your data is in a relational database, and I'm a data scientist. I'm tasked with building a recommender system. So would this technology be able to do a first pass recommendations model?
This technology would allow you to build state-of-the-art recommender system.
Oh, really?
Because
so you have actual users doing it?
I have actual users doing it.
Wow.
I can tell the story. So, for example, one of the users of this in the recommender system space is DoorDash. The use case is restaurant recommendation. Right, it's a flagship problem for DoorDash internally.
Oh yeah. This is one of the most important things that they do, right?
Exactly, right. And the use case specifically is try something new. So recommend a restaurant you never ordered from before. After we implemented this technology, it was a 30% improvement over the existing internally built model, right? And this was a flagship model. It was not somebody, at DoorDash woke up yesterday, let's build a recommender.
In this case, they hooked up your technology to their data, and pretty quickly they got to this 30%.
So what they did is as everything, it takes a couple of iterations, but maybe it took a month or two. So it was very short, but essentially the idea was, what are the tables we need? It was very easy to experiment with different data. Maybe, first we started with users, orders, and restaurants, but then very quickly was like, oh, why don't we also include the user behavior data on the website? And that was another table. And then it was like, okay, we have restaurants, but maybe geography is important. Let's add the geography table as well. And as this schema was curated, then the next step is to decide what's the objective function, what's the predictive task you want to do. Are you predicting, let's say, orders next week, next month, in the next 48 hours? So we tested, played with that as well, but the platform allows you to do this kind of exploration very quickly. And then we measured the accuracy, and it was a humongous lift.
And what you just described there is essentially no code, so it's all just prompting.
I mean, you prompt through code. So at the end, you use an SDK to write these things. I wouldn't say it's just prompting. Is data schema organization.
Yeah.
It is about deciding what is the proper predictive task. There is, as you are here, this is a fine-tuned model because you really care about accuracy.
So you still need data scientists.
You need a data science operator who does this. Yes, exactly. This wasn't just prompted. This is fine-tuned because it's a super high-value task. And, the benefit to DoorDash in this case was in hundreds of millions of dollars of, additional food orders because recommendations, notifications are now more accurate.
And then once they build the recommendation model, easy to deploy.
It is easy to deploy. Actually, that's a good point. The deployment with this type of technology also gets easier because all you need to do is refresh the raw data.
And then,
right? So
what about latency?
Good point. So latencyy is the following. You can do online inference over this graph. And of course, that has, 100 millisecond type response. If you want shorter, what you can always do is you can kind of use the model to pre-materialize the embeddings and then do the either exactly you do batch inference and then you do the real-time scoring, in 10, 15 milliseconds based on those embeddings with a very efficient model. So both are possible. It just depends on the application and on the requirements.
So I'm assuming that you also have a class of users who are just prompting.
We have a class of users that are prompting, but actually, to honestly say, where we see the most benefit is in these sophisticated
Data science
organizations.
I see.
And the reason for that is that sophisticated organizations can measure value very quickly. Right? Like with less sophisticated ones, it's more like, oh, some data scientist feels they want to do something from ground up with open source, and they keep doing that, right? While I would say in more sophisticated organizations with proper A/B testing and so on, it's very easy to prove value, or it's easier to prove value. The bar, of course, is much higher. Like I just gave you the DoorDash example, but they are sophisticated to say, hey, look, this is actually providing this much value. We are going to do this. So not only DoorDash, right? Like for example, another use case is advertising models at Reddit, right? These are large scale.
Yeah.
Flagship models, right? Like it's about predicting whether user is going to click an ad. That's exactly what drives revenue. That was another amazing improvement. It was like 4 or 5 years of improvement of what they would do internally if they would because every year they increase, model accuracy for about 1-2%. The team does, right? Because even with all the innovation and all the architectural changes and everything, but with this relational foundation model type approach, with this graph-based approach, it was like 4 years worth of improvement in a couple of months, right? So that's another very successful use case. And we see, examples at Coinbase, Expedia, and others, right?
Yeah, this is interesting because when I first read about you, honestly, my first reaction was, man, this sounds cool, but I don't know how they can sell this because they're going to sell it to the people who will get displaced. But then it turns out actually, from what you're describing, you're not displacing them, you're making them look like rock stars.
Exactly. I think this is not displacement. This is not about, hey, we can replace your job. This is a tool that the data scientists can do what the same data scientists are there to do, which is impact the business metrics, right? So with this type of tool, a data scientist becomes a rock star who's truly driving business outcomes, who is now 20 times more productive, is able to explore more, it's able to think more about how do I model here, what do I do here, and impact the business downstream. So exactly, I think you said it very nicely. It gets from grunt work to being a rock star.
So you've mentioned fine tuning. So in foundation model fine tuning, the typical workflow is here's some labeled examples: prompt, desired output, prompt, desired output. Upload it to some fine tuning service. Go away, come back. You have a fine tuned model. So what is the workflow for fine tuning a Kumo model?
Great question. So the way the fine tuning works is that you specify the task, you specify the predictive task. The beautiful thing is that a lot of these tasks, if you think about churn recommendation, they are temporal, meaning you kind of can slide through time, pretend that the time of now is kind of moving forward. You can look into the future, what truly happened, to have the label, and then you can use the past to predict that future label. So basically the point for fine tuning is that we can automatically generate, based on the specification through this time traveling mechanism, a data set that is used for fine-tuning.
You generate the data set.
I mean, data set. We generate the labels based on the time travel through the original raw data set. So you don't have to be doing even that manually. Of course, you can automatically generate it, and you can modify it and clean it if you like as a data scientist, but you don't even have to do that. You can just say, predict me this thing, and we say, oh, you are predicting 30-day churn in the future. Churn is you are predicting the count of transactions being 0. Okay, let's now kind of have this 30-day sliding window over all your data, and that will define the labels. Let's create the subgraphs in the past to predict the label in the future. And that generates the fine-tuning examples that then the platform uses.
And what's the typical number of examples you think that would make for a good fine-tuned model? I guess depends on but
that's a great question. We see that the range can be quite humongous. We can do well with 1,000 examples on the low end, all the way to tens of billions. If you think about Reddit, all its users, all their clicks, all the posts, all the votes, that's humongous.
The key is I don't have to generate it, right? So I just describe.
The key is you don't have to generate it.
Yeah.
Exactly. You describe the task, you point me to the raw data, and the platform figures out the rest.
Interesting. So obviously, I'm a data scientist. I work with structured data, but that's not the only thing I'm responsible for increasingly, right? So unstructured text, I don't know, semi-structured data. So is there something on your roadmap that will expand the utility of Kumu beyond structured?
That's a great point. So even now, I would say, we deal really well with unstructured data as well, as it is part of tables, right? So you have descriptions, strings, conversations, you have images, all that can be used, comments, all that can be used to build these predictive models, right? So Kumo is about building predictive scoring, forecasting type models. It's not, we don't do document summarization. We don't do, question answering over a static set of documents.
But we do in an e-commerce example where there's a lot of product reviews.
Then exactly, the platform can leverage those product reviews to make more accurate recommendations. Or we just worked with one of the we are working with one of the largest dating apps out there, and they are using Kumo to predict who's going to go on a date with whom, and their current system did not use images, so we were like, just let's add an image column here with images of all these people, and let's build it, and it was immediately 15% more accurate.
Right? You mean you actually leverage the images, so you use some sort of computer vision.
Exactly. So the image embedding, the image encoding now is part of the recommender system. And if you want to say who's going on a date with whom, then knowing how that person looks, non-surprisingly contains a lot of signal, right? So the beautiful thing is that with this technology, you just add another column to the table. You say, here's the image of the person. Here's and the platform takes care of the rest, right? So it's very easy to also build these multimodal predictive models that are using textual data, comments, images, and things like that, but for predictive tasks.
So if you were to rank the top 3 ways top 3 kind of families of use cases for Kumo, will it be forecasting, recommendation? What are those top 3?
Yeah, let me answer. I think where we see lots of traction, one is kind of in retail commerce, which is about user behavior type questions, right? Like recommendation, churn, lifetime value, and so on. Then another place where we see lots of value is on safety, fraud, financial abuse, abuse. So a lot of fraud models, any kind of bad behavior models, things like that, across social network, financial institutions, and so on. And then another place where we see lots of value is risk models, predicting all kinds of risks, about deciding whether to discharge a patient in the hospital, deciding to give, is this fraud in insurance industry, things like that. So these are the big, I would say, it's the retail, it's the media, and then this kind of fraud financial use cases.
So do you folks have some homegrown entity resolution kind of tool? Because basically, like I said, some of this data, like fraud, right? So I could be using multiple versions of my name and whatever, right? So is that part of the system, or am I responsible for that?
That's a great question. The way we would usually do this is we would like if we want to go that far to do this kind of entity resolution step, then the platform basically allows you to quickly build these entity resolution models as almost like a pre-processing models that then curate the data for the final model. So that's how we would do it. It's almost like a two-stage process.
It's in the platform.
The platform allows for allows you to do or to build entity resolution models, if that is. But what we see, because our data, our information is graph-based, then the need for entity resolution is actually smaller because these entities kind of get connected through the graph anyway.
Yeah.
And through this attention mechanism over the graph, the predictive model can kind of learn to do entity resolution on the fly as it is making a prediction. So you don't have to be doing entity resolution separately from the predictive task.
So as with any AI technology, right? So you have users. In order to engender user trust, you have to kind of explain, there's some sort of explanation for how you arrived at the decision or some transparency. So how do you do this for your user base of mainly data scientists?
That's a great point. I think explanation is critical because in contrast to business analytics, where once you have the result, you can kind of go back and verify it. In prediction, you cannot go back and verify it. You have to kind of wait for it to happen to see whether it was correct, right? So the importance of explanations is even higher. And what we have is a completely new approach to explanations, because our models, as they attend over the raw data, we can basically ask them, we can run them backwards and say, what did you attend over? So our models can go back to the raw data, raw tables, raw columns, rows, and say, this is the data I used to make this prediction. So you get this truly data-driven, data-rooted explanations. And now, of course, you can get them at the level of the entire model, where the model says, here is what I'm looking to make these predictions. And you can say, okay, yeah, this makes sense. These are the right signals to look at. If the model is looking at wrong signals, something is wrong and you can fix it. And also you can do it at an individual prediction level when you say, okay, here we make this recommendation. And you can then ask, okay, what events in the past, what structures in the past made me make this prediction? And with that, we can either present that to the user in a structured form. But what we see works really well is that we take this structured explanation plus the semantic model and put that into an LLM to generate a text-based explanation. And those explanations are actually easy to consume, easy to read, and really good. And non-hallucinated because they are truly done from what the model is attending over.
Well, you might as well, in the text explanation, also put charts in there if charts help explain what you did, right?
You could also, yeah, exactly, go beyond and present this in more graphical form.
And just say, here are the things that I used, features, and then there's a bar chart.
Mm-hmm.
Or whatever. So another obviously trendy topic in AI is agents.
Mm-hmm.
So how do you fit in the world of agents? And the reason I bring it up, Jure, is agents, one way to think of it is maybe you don't need a monolithic model. What you need is a model that mainly breaks down the tasks and assigns it to either smaller models or specialized tools even, right? So external tools like via MCP. So how do you fit in the world of agents?
That's a great point, right? Like one important thing of agents is agents need a decision power.
Yeah.
That decision power needs to be rooted in data, right? So we can basically be a tool for the agent to make predictions based on which it makes decisions, right? So very quickly, right? Like I would say the present generation of agents, they're mostly, let's reason over some static text and do something. But for the agent to be truly autonomous, reasoning over text is not enough. It needs to reason over internal structured data to make decisions, right? So for example, you could say, I'm an agent. I want to see which are the high, let's say maybe in an insurance industry, I'm an agent who estimates how likely, what are my top customers who are most likely to churn. Then I need to estimate what offer would I send them, and then I need to write an email and send that email, right? If you think about this workflow, there are two predictive problems here, or two decision problems here. One is, let's estimate the risk score of every agent, of every customer, and then for every of these high risk customers, let's go and recommend what is the best offer, the most likely offer they're going to take, and then let's write the email, right? And today, both these decision problems, the risk scoring estimation and recommendation, you would need a data scientist to manually solve, spend months, and only then this agent can do something, right? With the relational foundation model, agent can just query the database and say, estimate me the risk scores, select me the top 1,000 people who have the higher risk of churn. Now, for each of these people, recommend me what is the next best offer to give them.
By the way, you basically fit into the category. I mean, you do more than what the time series foundation models do, but I can use you as a time series foundation model, right?
You could use me as a time series foundation model because, of course, our
because it's
works.
Still relational data.
It's on a single table. But for example, where the benefit becomes is time series are not isolated, right? If you have a time series per product, maybe you have a product taxonomy.
Right.
But now our model not only learns from the target product time series, but through the product taxonomy can attend over time series of other products. So it can start to borrow information from other time series, correlated, related to the target product, to give you much more accurate time series forecasts.
All right. So now we're at the stage in the podcast where I have to ask you, what is open source? What part of Kumo is open and what is not?
Yeah, great question. So we are authors of the most popular open source graph learning library called PyG, or PyTorch Geometric. So pyg.org is where people can use this. Of course, I would say graph learning, putting that in production is super hard. It requires years of engineering to do it.
And also the way you describe it, it seems like that's only one aspect of the offering, right?
Exactly, right? So doing that, so what we did at Kumo is first we built a large-scale production-ready graph learning platform that now anyone on the planet can use. On top of this, we also built a foundation model that is accessible through SDK, through MCP, and we have that available for people to use through our servers. We are not able to open source this because the infrastructure.
Open weights,
even open weights is infeasible because you need all our infrastructure to run this, right? You need the graph learning infrastructure to run the graph learning model. So if I open weight the graph model, you need our infrastructure to run it. So because of this coupling, rather than say we'll open source it, we just say, here are the APIs, you can use it, you can experiment with it for free, you can use it for free, and then once you start getting value out of it, we can talk about paying. But trying this out, playing with this is free, people can use it. And the reason being is that, it's a special infrastructure plus a special model architecture.
By the way, I forgot to ask you, I don't know how I forgot this, but foundation models, obviously, like as you mentioned, you trained the foundation model. So what was the data?
Great question.
Yeah.
The data is, it's interesting. It's actually some open data on the web, but they need to be databases. It needs to be multi-tabular, right? Single tables do not work here. And then what we do is a lot of synthetic data generation, a lot of data augmentation, because what you need to do is you need to teach this transformer how to how to learn from patterns, right? Because then when you give it the in-context examples, it needs to kind of learn from those in-context example and generalize to the unlabeled example. So the key is to think of this as teaching the transformer to learn and recognize patterns, right? So it's not so much about ingesting data semantics. It's really about pattern recognition to some degree.
And then the typical usage of it is you pointed to data that's relatively it's already being used by data science teams for analytics and forecasting, right? So in other words, you're not going to hit the ERP system which has 10,000 tables, right? So the typical data scientist already goes to a data warehouse or lakehouse or something, right?
Exactly, we would connect to that. Exactly, it's data warehouse.
So the type of data you simulated using synthetic data more or less kind of mimics
Data warehouses.
that kind of data warehouse star schema kind of thing.
Exactly, whatever the schema is, right? And the platform, can easily connect to your Snowflake, Databricks, BigQuery, Bigtable, S3 files, Parquet files, Iceberg, whatever it is, right? You just say, here's my data, these are my tables.
Can you give an intuitive explanation for how does this work so well? Because in the following sense, right? So if you just take univariate time series forecasting, well, there's infinite many patterns of time series, and I mean, you can't possibly have seen every possible time series out there, right? So look at just the Internet of Things. There's so many devices out there. So what's the intuition for why this works?
I mean, that's a great point, right? Like, what I'm saying and kind of what I'm promising, it seems a bit crazy or unbelievable and magical. And we were surprised as well. It's unclear why should this even work. And I think, two answers. I think maybe the first answer is and I think the truth is a combination of two things. First is that transformers, neural networks seem to have this kind of generalization ability where they are going to go kind of beyond what they were trained on, right? Somehow in some embedding space, they're able to put kind of similar things together so that it's possible to connect them and generalize between them. So I think that's one part of the answer. And then I think the other part of the answer is, maybe the world is less complicated than we think, right? Like in some sense, if you think about, maybe the best thing to think about is Taylor expansion, right? Like to the first approximation, the world is linear, mostly, right? So I think maybe the universe is more orderly or less complicated to say, oh, there is arbitrary functions, gazillion of arbitrary things, right? Probably not. Right? So I think with these two, that there is order in the data and that those patterns, everyone is unique, but at the generalization level, maybe they collapse to a smaller set of these eigen patterns. I don't know, maybe I just invented a new word, right? You call it eigen patterns or something. Maybe that's what the model is learning. Together with this generalization allows you to do this.
I guess the litmus test, Jure, is having worked as a quant in a hedge fund, is can I use this in kind of the quant setting to build trading models, right? So that would be interesting.
That's interesting. I think that's interesting.
I don't know if anyone listening will attempt to do it, but because to the extent that that data is relational, right? So maybe you have some earnings reports that you can embed and store in columns and stuff, but I don't know. So what's your intuition? Will it work?
I think it's interesting, right? I think what this allows you to do is really learn from these, second, third order correlations. And, the economy is a network of interdependent, intercorrelated parts.
In many ways,
I think that
you can put all of that data in a relational database and then maybe embed some of the earnings reports and
Exactly.
And
I think that will give
suddenly
you,
this system will do all of the work for you, right?
that is true, right? So at that level, I think you can get an edge, right? At the same time, can we predict how some dictator is going to wake up tomorrow on what they are going to do? Certain things,
Yeah.
are also unpredictable. But from saying, okay, given the data we
The
have,
baseline.
what is the signal we can extract? I think this technology is the way to extract signal from structured data
And also
to maximum degree.
the benchmark is the human. What is the human quant able to do? And can I
Exactly. The benchmark is the human. Of course, maybe one thing you could do is to say, okay, why don't I unleash an LLM? And LLM is going to go through this and build these models and so on. But those take time.
And one
right?
last,
And it's unclear. They are subhuman in performance.
And one last example I'm going to throw out there is sports betting. All these people doing sports betting, right? I mean, all that data, the scores, the historical averages, all of that is in a relational database, right?
Exactly. That would be another way how you could get, of course, all these things are ultimately uncertain, right? So predictions come with uncertainty intervals.
My baseline is human.
Your baseline is human, exactly. And that we can do better, right? I think is the point.
All right. So listeners, we are not investment advisors. Do not take our advice, but you go ahead and try Kumo. And with that, thank you, Jure.
Thank you so much, Ben.